Welcome and hello. This is a support video for HEC HMS, and in this video I'm going to be discussing downloading spatial results. The question came in about how to download results in the form of a raster file so that they could be analyzed for runoff coefficient in each grid. And each grid is referring to the spatial results grids that we're seeing right here in the simulation. I don't have one particular great answer for this question, but a number of ideas came to mind that I'm going to share with you in this video to hopefully help you get started in this pursuit of extracting spatial data on a grid basis from your HMS simulation so that you can use it in GIS applications, Excel, any other database that you wish. All right, so let's go ahead and get started. The first step is to, of course, build and run your model and save and view the spatial results. I've already done that, and I've already covered that in previous lessons. For instance, support video 5 talks about the different requirements that you will need in your model to be able to view spatial results within your subbasins on an individual grid basis, like we're seeing on the screen here. And I'll also link to exercise 11 for viewing spatial results. And I probably have a few other examples in my lessons or exercises somewhere. All right, so let me just show you the model real quick. It's a very simple model. If I click on the subbasin tab here, I'm using the Mod-Clark transform method and an initial and constant loss method. So the transform method has a time and concentration and storage coefficient. This is true for the entire subbasin. And then the loss method has an initial loss and a constant rate of infiltration. For the meteorologic data right here, it's called MET2. It's using interpolated precipitation, and that uses three different gauges, A, B, and C. I've got A right up here, B, and then C. And what's going to happen is I've staggered the peak of the precipitation. So let me just show you the results first. And then over here in DSS view, here's my precipitation data. And then here is gauges A in blue, B in light blue. Oh, I guess that's C. Okay. And then C is right here. So the peak of the precipitation is staggered. It's going to be A and then C and then B. And then back to HMS, they are located A and then C and then B. So I'm just going to scroll through the results. This is precipitation in the first few hours, which is strongest in the northwest. And if I can continue clicking through, now we have the strongest precipitation down in the southwest. And then after that, it's going to be over here in the southeast. So there's that right there. If I go ahead and right click and plot the spatial results, what I'm looking at here is a plot of the incremental precipitation over the course of the 3-day simulation. And this is for the location that I selected over here in the southeast corner of my subbasin. So we see a minor contribution from the first two peaks, but a major contribution from the third peak because it's using a inverse distance method here for the interpolation method. However, if I look at the same data over here in the sort of the northwest corner, this is going to have a strong contribution here in the first peak and then a smaller contribution in peaks 2 and 3. And then over here in the southwest, there should be a contribution primarily here on the second peak. All right, so there's that data. If you want to extract the data from this plot, again, our variables are incremental precipitation, incremental loss, and an incremental excess, where the precipitation minus the loss will equal the excess, which is the quantity of precipitation that's contributing to the runoff. If I select incremental precipitation first and say I want this location right here, if I hover, that's 0.27 inches, and that's the amount of hourly precipitation that's occurring at the current time step, which is right here on the slider bar. Let me just advance it forward. Okay, so that is the first hour of day 2. So this is July 2. This is for July 1st, 2nd, and 3rd. I didn't mention that. And then here's the second hour of July 2, the third hour of July 2. If I start from the very beginning, we start at the first hour of July 1, second hour of July 1, 3rd, 4th, 5th, 6th, and 7th, 8th. We'll just stay right here on the 8th hour. If I hover over this particular cell, it's telling me 0.22 inches. Again, that's only on the 8th hour. If I want to see all the data, right click. That 0.22 is probably right here. So if I advance it another hour, it'd be 0.3 or maybe here. If I want to get the actual table data to extract, I can go File, Tabulate, and then here is all 72 hours worth of precipitation data. Now, this is not the most efficient way of extracting data because at least in my case, I think it's 66 different cells in this grid. You don't want to be making this operation of right click and then file, tabulate, and then copying this data into your Excel spreadsheet or into your GIS attribute table for every single grid in your grid, which is for me is 66, times every single variable, which in this case you may want your precipitation, the loss, and the excess precipitation. But I'm just letting you know that that is an option. We can also view results and get some similar numbers by clicking on the Results tab here in the Watershed Explorer, and then expanding the Simulation Runs folder. And my particular simulation run was called Run 1, just the only simulation run I have. So I'll click on that. And then if I click on Subbasin 1, this is going to provide us data, but it's going to be for the entire subbasin, not the individual cells. So this is a little bit off topic from my original intent of getting the individual cell data, but I wanted to describe it while we're already here. Now, the variables that I may want to be most interested in here is going to be precipitation. So I'll click that with a single left click on the mouse button, hold down Control, and then click on precipitation loss, and then click on excess precipitation. Now I have sort of a preview plot down here, but if I click on the graph button over here, I can see these values. And if I wanted to change the color, I can go up to Edit, Plot Properties. We'll keep it red, but make it a little bit thicker. And then for precipitation loss, I'll make that a solid line. And then we'll make that thicker as well. We'll change the color there to make it dark green. And then for excess precipitation, again, a solid line, but we'll make this, how about light purple? And again, make it a little bit thicker. Apply, okay. And here are those depth values of precipitation. Again, red here is the total precipitation that falls from the sky. Precipitation loss is in green, so red minus green will be the amount of precipitation excess, which is purple, that contributes to the runoff. If you want to get these values, the actual numbers, you can go File, Tabulate, and then here is the table of values. Here's the total precipitation minus the loss is going to give us the excess precipitation for all 72 hours of data that we have. Take notice that we don't have any precipitation in the second half of the simulation, so that's why there's a bunch of zeros there. But if I had a larger watershed or a larger time of concentration or something, or a different storm event, then I could very well have data down here. Okay, but keep in mind, this is not the individual grid cells. This is for the entire subbasin. Now, you may have particularly small subbasins, in which case this sort of data is acceptable, but maybe not. All right, so let's head over to DSS View. And now we're going to open up the DSS file called Run1. This is the DSS file that's named after the simulation. So if I go back to HEC HMS, under the Compute menu, I have Run1. So when you run a simulation, HMS will save a DSS file with the Run1 results, which is what I'm seeing in the screen right here. And here is my project directory, and run1.dss is right here. All right, so that's what I have opened up. I already have the 3 paths that I'm interested highlighted. So all I need to do is click on the plot button. And then here is the same plot that we saw before. Of course, the colors are a little bit different. And I can also get the table data, which is right here. But it looks like the order of the columns are a little bit different. So this is total precipitation, loss, and excess. Again, this is for the entire subbasin, not the individual grid cells. If you do want to extract this data, though, you could do that by just selecting this data. You could probably just right-click, Control-C, Control-V into Excel, or File, Export, and then there's some export options here. So I'm not going to explore that, but just let you know it's not difficult to export data from DSS View. The other DSS file I want to look at is the meteorologic data, and this is going to provide us the individual grid cell precipitation data. In HMS, if I click on the Components tab, my meteorologic model is called MET2. I originally had a MET1, and then I revised it with MET2. So we're looking at MET2. If I go to the project directory, here's my MET1. Don't worry about that. Here's MET2.dss. That's what we're going to open up. And I already have that open up in my DSS view. And what you're seeing here is going to be 72 different records for precipitation. This is the incremental precipitation, the total precipitation, but it is recorded on an individual grid cell basis. So if I just Control A, select all the fields, and then click on the Plot tab, here's the dialog box that popped up. And then this is only the first hour. So down below here, I have 1 of 72. I also want to direct your attention at the top. There's tabs for grid display, grid info, and detailed grid info. So the grid info is sort of a subset of the data from the detailed grid info. And then the grid display, of course, shows you the actual values. This is the hourly precipitation. You're seeing 0.014, 0.013, Brown and even white is the highest colors. Brown represents the highest values, green represents the lowest values. And again, this is just the first hour. So if I toggle through this simulation, there's the second hour, third hour, fourth hour, fifth hour. We're seeing precipitation in the top left corner, and then we're going to have more precipitation down here in the bottom right. This is the 13th hour, and then later in the first day over here in the southeast corner. Now, for the second half of the simulation, you're going to see all green because all the values are 0. Okay, let me back that up to the beginning and then just go ahead to maybe the fifth hour. What you're seeing are individual grid cells, and this represents the grid size of the precipitation data that I specified when I went to interpolated precipitation. Excuse me, if I go to the subbasin and then I click on the discretization tab, I'm using a cell size of 1,000 meters right here, which basically means each cell is 1,000 meters by 1,000 meters, or 1 kilometer squared. If I click on the grid info tab, I see that cell size of 1,000 right here. It also shows me that the grid extents is 10 by 8. So I'm going to see a total of 80 cells here. It's 10 across the top and 8 down. Now, my subbasin won't be using all 80 cells. I think I counted 66 total cells or partial cells. So what you're seeing here is the outer bounding rectangle, and I should be able to match up the numbers. So for instance, if I go to HMS and then I go to the fifth hour, so 1, 2, 3, 4, 5 right here. Let's just go ahead and do a spot check. I have precipitation values of 0.19, 0.18, 0.16. Okay, so let me go back to DSS view here. And then let's see, I'm looking for a 0.19. Yeah, so this would be 0.19, 0.18, and 0.16. Of course, this is rounding to the nearest 3 decimal places. Now, unfortunately, I don't have a quick and easy way to extract this data from DSS View, but I'll show you how to do that using an HDF5 viewer. I could possibly write a Python script to extract that data, save it to a text file, but again, this is only for precipitation data. I don't have a part C that says precipitation loss or precipitation excess. It's only for precipitation data because remember, this is coming from the meteorologic model. It isn't considering any of the details of the subbasin. All right, so now I want to introduce a HDF5 viewer. So if you have an HDF5 viewer already installed, go ahead and open that up. All right, here it is for me. This is HDF View 3.3.2. If you don't have this program already, you can download it from this web page, the HDF5 group. The web domain is support.hdfgroup.org/downloads. I'll go ahead and leave a link to that in the description of this video. And then what you're looking for is HDF5. This is the libraries and tools. I just downloaded HDF5 View, which is this one right here. So go ahead and download it and install it, and then bring that up to screen when you're ready. There's also HDF4 and a few other previous versions if you're interested. All right, so once you have it up, go ahead and click open and then navigate to the results directory. So here's my project directory, and then inside that, I have this folder for results. And then I have this .h5 here with the name of the simulation, run1.h5. So this is the file that I'm going to open up in my HD view program. Okay, I have navigated to my project directory. I'm going to go down to results, and then here's the only .h5 file in that directory. And boom, the file is open. Over on the left here is the menu. So I want to expand results, expand subbasin 1. And then what I have is data for cumulative excess, cumulative loss, incremental excess, incremental precipitation. This incremental precipitation is the one I want, our IWE precipitation, as well as excess. So the difference would be the loss. And if I double click, it's going to bring up a table here of data that looks similar to a spreadsheet application. What I'm looking at here is the hourly precipitation data in each cell of the simulation, where in this case, each row represents one time period, or 1 hour in my case, because I am using a 1 hour time step. So the first row, second row, third row is the first hour, second hour, third hour. And then this first column here represents one cell grid on my map. And then the second column here is a different cell, third cell, and fourth cell. So anyway, the total domain of time should be 72 hours. So if I scroll down to the bottom, I see 71, and that's a total of 72 because the numbering starts at 0 here. And then for the number of columns, this represents the total number of cells in my grid. So if I Scroll all the way to the right using this horizontal scroll bar on the bottom. 65 for a total of 66 cells, which makes sense because I believe there's a total of 66 cells or partial cells in my grid. Not an entire 80, but most of 80, because we saw a total of 80 when we were looking at this grid right here in the DSS data. Now, a good question is, which cell am I looking at? 61, 60, 59, and so on. How does that match up with this particular plot right here? I don't have a good answer for you on that one, but I mean, if I looked into it, I'm guessing that it would probably be reading left to right, top to bottom, or top to bottom, left to right, after identifying the first few cells in the HDF5 viewer and then matching them up with this data right here. Probably wouldn't be too hard to identify the pattern that's being used. To extract this data, I think you can just you may be able to Control C, Control V, but there is actually an export method. If you click on Import Export Data, export data to, and then text file. I'll just call this precip, and then I'm going to save this to my desktop. So desktop and save. It's just going to save as a text file. So let me go ahead and bring that up. Here is the data. Here's the first row of data, and that should have 66 values representing the first hour. And then here is the second row of data in this text file. It looks like it's just space delimited. This represents all of the hourly precipitation data for the second hour of the simulation and so on. From here, you can import this data into Excel, into a database program, into your shapefile attribute table, or your raster file, excuse me. So I'm not going to go into too many details. The purpose of this video was to just sort of give some ideas to anyone who's trying to extract the individual results data from an HMS file that involves spatial data, or rather the spatial results in an individual grid basis. So again, this is the precipitation. I can close that. This is the incremental excess is what it's called, referring to the amount of precipitation that was not infiltrated or was not lost to infiltration. So of course, these numbers are going to be a little bit less than the numbers we saw previously. You can see the first 3 hours, it looks like, is there's no runoff because all of the precipitation was absorbed or lost from the loss method. But then later on, we do have some runoff for each of these individual cells. So if you're looking to calculate the runoff coefficient, you can use the numbers here. And one last thing I wanted to mention was in HMS, we can also export the subbasin as a shapefile and the individual discretization as a shapefile as well, and then load that into our GIS program, which can help facilitate this particular viewer's question with regard to creating a raster file. So to do that, I'll go up to GIS. Of course, your model or your basin already needs to be geo-referenced, and then click on Export Layers. Now your different options here are subbasins, discretization, breakpoint, and identified streams. I'm interested in the first two, subbasins and discretization. So I'll click on subbasins, click next. And then again, I'm just going to save this onto my desktop for now. I'll call it subbasins, and then it's going to save as a .shp file. I'll click finish, and then there's that file, or files with the projection. I'm going to do the same thing with the discretization. So I'll go up to GIS, export layers, select discretization, next, navigate to where I want to save that. I'm just going to call it grid.shp and then click save and finish. So that's saved right over there. And lastly, what I'm going to do is open up QGIS, and then that's opened up right here. I'm going to drag in my subbasin shapefile. So here is my subbasin. This is the outline of it. And down at the bottom of the screen, you can see we have the coordinate system for northing and easting, which is consistent with what we were using in HMS. And lastly, let me drag in the grid shapefile. So we have the individual grid shapefile with which I can toggle on and off. That is working in concert with the subbasin shapefile. Okay, so you can go ahead and load in your data that we extracted from the HDF5 viewer or whichever method you use to extract data. And again, this is a support video just to give my viewers an idea of how to extract individual cell data from a gridded spatial results in HMS to later use in future analysis, whether it be Excel, database, or some sort of GIS raster file.